Welcome to IIOCS.com Food Tech Club. Today's topic is food preservation by the method of irradiation. Food irradiation is the process of exposing food to controlled levels of ionizing radiation to kill harmful bacteria, pests, or parasites, or to preserve its freshness. The food irradiation is also called as cold pasteurization as it kills harmful bacteria without using any heat. Food irradiation is a technology that improves the safety and extends the shelf life of food by reducing or eliminating microorganisms and insects. Like pasteurizing milk and canning fruits and vegetables, irradiation can make food safer for the consumer, that is, without using heat. The Food and Drug Administration (FDA) is responsible for regulating the source of radiation that are used to irradiate food. Let us look at the purpose of irradiating the foods. So the primary purpose is to prevent any kind of foodborne illness, that is to effectively eliminate organisms that cause foodborne illness such as salmonella and E. coli. Next is preservation, that is to destroy or inactivate organisms that cause spoilage and decomposition and further extends the shelf life of foods. Next is control of insects. So that is to destroy insects in or on tropical fruits imported into the United States where this irradiation is mostly being used. Then irradiation also decreases the need for other pest control practices that may harm the fruit as well as our health. The next purpose of irradiation is to delay the sprouting and ripening of fruits, that is to inhibit the sprouting, example in potatoes, and ripening of fruits to increase the longevity of the fruits. The next purpose is to sterilize the foods. So irradiation can be used to sterilize foods which can then be stored for years without refrigeration. So this sterilization is also useful in hospitals for patients with severely impaired immune system, such as patients with AIDS or patients who are undergoing chemotherapy. Foods that are sterilized by irradiation are exposed to substantially higher levels of treatment than those approved for general use. So for sterilization, the dose of irradiation is little higher. Let us see how the food is irradiated. Many of the traditional methods of processing make use of energy in one form or another. That is, the heat is used in canning and sun drying, for example. Or if you take in freeze drying and all, you are removing the heat there. So there also you are reducing the temperature and preserving the food. So in case of food irradiation, it employs a particular form of electromagnetic energy, the energy of ionizing radiation. So the three sources of radiation approved for use on food preservation is gamma rays, X-rays, then electronic beams. Gamma rays are emitted from radioactive forms of the element cobalt 60 or from cesium-137. So gamma rays are emitted from cobalt-60 and cesium-137. Whereas X-rays are produced by reflecting a high energy stream of electrons of a target substance, usually one of the heavy metals, into the food. So through any heavy metals, the high energy stream of electrons are reflected. The next type is electron beams. Electron beam is similar to X-rays and is a stream of high energy electrons propelled from an electron accelerator into the foot. Okay, these are the three types of irradiation sources. So X-rays, which are a form of ionizing radiation, they were discovered in 1895. Radioactivity and its associated ionizing radiations like alpha, beta and gamma rays were discovered the following year. So after the discovery of X-ray, it was followed by other rays like alpha, beta and gamma rays. Yeah. Let us see the mechanism of irradiation. The preservation action of ionizing radiation is due to both primary and secondary effects resulting from interaction of radiation with the molecules and microorganisms present in food. Let us look at the primary effect. The incident radiation interacts with the atoms and molecules present in food and cause ejection of electrons. So electrons are excited here. This leads to ionization and dissociation of the molecules. The ejected electrons cause further excitation of molecules present in food. So it's like a chain reaction. The incident radiation excites the molecules, the electrons in the food, so that further excites another molecule in the food. Then comes the secondary effect, so where you can see the radiolysis of water. Since water is present in almost all the foods, either in free or bound form, an understanding of chemical changes which water undergoes is important. Gamma rays excite and ionize water and other molecules along their track, giving rise to excitation, ionization and formation of free radicals. These events contribute a great deal to the secondary effects of gamma radiations. So in the secondary effects, basically the water molecules are excited, ionized and free radicals are produced. Yeah, so the mode of action by which the microorganisms are killed by using irradiation is as follows. Irradiation can directly impair critical cell functions of components like DNA and indirectly form radiolytic products or free radicals from water, which are responsible for 90% of DNA damage. Irradiation results in a variety of changes in living cells based on the dosage. So about this we will further study in the coming slides. Okay, so let us see the nutritional quality of irradiated foods. Irradiation does not considerably raise the temperature of the food, and nutrient losses are small and often significant as compared to other methods like canning or any other method which uses high temperatures. So due to the lower temperature in irradiated foods, the nutrients are retained pretty well when compared to other methods. Macronutrients like carbohydrates, proteins, and fats undergo little change during irradiation even at doses over 10,000 gray. So we will be learning more about this doses of irradiated foods in the further slides. So even at higher irradiation doses, the macronutrients won't undergo any changes. Similarly, the essential amino acids, minerals, trace elements, and most vitamins do not suffer significant losses. When it comes to vitamins, the vitamin losses can be minimized by irradiating the food in frozen form or by packing it in an inert atmosphere such as under nitrogen. Four vitamins are recognized as being highly sensitive to irradiation. Those are vitamin B1, vitamin C, then vitamin A and vitamin E. However, vitamin B1 is even more sensitive to heat than irradiation. So for vitamin B1, irradiation is a better option than any other heat treatment. Yeah. Let us see the radiation sensitivity of microorganisms. So we saw the mode of action of irradiation on organisms, right? So in detail, let us look at the sensitivity of microorganisms to irradiation. Exposure to radiation causes structural and functional changes in macromolecules of the microorganisms, thereby leading to cell death or injury. DNA or RNA is the most important target for radiation inactivation of living cells. Radiation acts on DNA in two ways, as I told you before, that is direct and indirect ways. In direct action, DNA absorbs radiation and is damaged. The damage to DNA can be of different varieties. So single strand of the DNA can break or both the strands can break. Alteration of the nitrogen compounds can happen, like alteration of purine or pyrimidine bases, nitrogen bases, or interchain bond formation can also happen. In indirect action, other molecules like water and the free radicals thus produced react with DNA, absorb the radiation. Okay, this is the secondary effect which we had studied. Okay, let us see the radiation doses required for the irradiation of food. The quantity of radiation energy absorbed by the food is the most critical factor in food irradiation. Often, for each different kind of food, a specific dose has to be delivered to achieve a desired result. If the amount of radiation delivered is less than the appropriate dose, the intended effect may not be achieved. Same wise, the vice versa can also happen. That is, if the dose is excessive, the food product may be so damaged as to be rendered unacceptable. The special name for the unit of absorbed dose is the gray, which is written as GY. It is the unit gray is defined as the mean energy imparted by ionizing radiation to the matter per unit mass. So gray is nothing but the mean of the energy imparted by ionizing radiation to the matter, the food material per unit mass. Okay. 1 gray is equal to 1 joule per kilogram. So an older unit of radiation measurement, the rad equals 0.01 gray. So before, for radiation measurement, rad was used. So that if you compare with rad, it is 0.01 gray for 1 rad. At present, the dose of radiation recommended by the FAO or WHO, FAO and WHO Codex Alimentarius Commission for use in food irradiation dose does not exceed 10,000 gray, which is usually written as 10K gray. Okay, K is 1000 here. The radiation dose ordinarily used in food processing ranges from 50 gray to 10,000 gray and depends on the kind of food being processed and the desired effect. So for every food, the lab analysis should be done to see to what extent or to what dose the irradiation can be done. Okay, it is for food, it is between 50 to 10,000, 50 gray to 10,000 gray. This is actually a very small amount of energy equal to the amount of heat required to raise the temperature of water by 2.4 degrees Celsius. The 10,000 gray, the maximum amount which we can use for food, that is equal to the temperature required to raise the temperature of the water, the energy required to raise the temperature of water by 2.4 degrees Celsius, only that much. Okay, so that much of heat is equal to the 10,000 gray. Yeah, so let us look at the doses requirement in various application of food irradiation. So we have 3 levels of doses. The low dose, that is up to 1 kilo gray, and medium dose is up from 1 to 10 kilo gray. High dose is between 10 to 50 kilo gray. 50,000 gray. In low dose, low dose is used for inhibition of sprouting. There we use 0.05 to 0.15 thousand gray. Then that is used for potatoes, onions, garlics, ginger root, etc. So this is to inhibit sprouting. Next level is insect infestation and parasite disinfection. That is between 0.15 to 0.50. So it is used in cereals, pulses, fresh and dried fruits, dried fish and meat, fresh pork, etc. And the next one is delay of physiological process like ripening. For that 0.5 to 1 is used. Then this is used in fresh fruits and vegetables. Next comes the medium dose, that is 1 to 10 kilogram. So the first one is extension of shelf life, that is done in fresh fish, strawberries, etc. So the dose is 1 to 3 kilogram. Then elimination of spoilage and pathogenic microorganisms. The dose is 1 to 7 kilogram, usually used in fresh and frozen seafood, raw or frozen poultry and meat, etc. Next is improving technological properties of food like increasing juice yield in grapes or reduced cooking time in dehydrated vegetables. For this purpose, we can use 2 to 7 kilogram of radiations. The next is high dose radiation between 10 to 50 kilogram. So in industrial sterilization it is used, where it is associated with the use of a little bit of heat also, okay, in industrial sterilization. So the dose is between 30 to 50 kilogram. Meat, poultry, seafood, prepared or processed foods, sterilized hospital diets, all these are done with this high dose. Next is decontamination of certain food additives and ingredients. So that happens between 10 to 50 kilogram, and it is used in spices, enzyme preparations, natural gum preparations, etc. So these are the dose range for different food varieties. Okay, let us look at the sources of ionizing radiation. There are two types of radiation source which can satisfy the requirement today for irradiation. So one is by machines and one is man-made, and the other one is man-made material. Although they differ in the method of operation, both types of source produce identical effects on food, microorganisms as well as insects. So let us look at the machines, the irradiating machines. Machines called electron accelerators produce electron radiation, a form of ionizing radiation. Electrons are subatomic particles having very small mass and a negative electric charge. Beams of such accelerated electrons can be used to irradiate irradiated foods at relatively low cost. This cost advantage is offset, however, by the fact that accelerated electron beams can penetrate food only to a maximum depth of 8 centimeter, which is not deep enough to meet all the goals of food irradiation. So though it is cost effective, the penetrating power of this electron accelerators is very less. So that's why it cannot be used for all kind of foods. Accelerated electrons are therefore particularly useful for treating grain or animal feed that can be processed in thin layers. Electron beam irradiation is particularly suitable for these applications. So we had studied that electron beams are produced by electron accelerators, right? So electron beams are particularly suited for this. Yeah. So another type of machine source of ionizing radiation is the X-ray generator. An X-ray is a wave form of energy similar to light. Unlike accelerated electrons, X-rays have great power to penetrate some materials. But as the early experiments found, converting electricity into X-rays is a very inefficient, hence expensive operation. So when compared to the other, that is electron beam accelerator, so that when compared to that, the cost is higher for this X-ray generator. The X-ray machines available for food processing have generally been adapted from those used in medical and industrial radiography and are not well suited to supply the power needed for food processing. Though recent developments suggest that these problems of cost and power can be solved by new advances and inventions in the new type of X-ray generators. Next is man-made irradiation sources. Man-made radionuclides constitute the other main source of ionizing radiation. Radionuclides are radioactive materials that, as they decay, give off ionizing gamma rays that can be used for food processing. One radionuclide that is readily available in large quantity is cobalt 60. So we had studied it in the previous slides that cobalt 60 is a source of gamma radiation, which is produced by exposing naturally occurring cobalt 59 to neutrons in a nuclear reactor. The availability of another radionuclide is cesium 137, a byproduct of nuclear reactor operations. It is limited and it is not used widely at present. So cobalt 60 is the one which is available in large quantities. Gamma rays from either of these radionuclides will penetrate deeply enough to meet virtually all food irradiation needs. The cost of man-made radionuclide sources is considered acceptable for industrial food irradiation in view of the great versatility and penetrating capacity of the gamma rays. Okay, so we saw the sources of the irradiation, and now we'll look into the process of irradiation, how these sources are used for irradiating foods. So like all other industrial methods, we have two types of processing method. One is batch and another is continuous. So in batch facility, as the name tells, a given quantity of food is irradiated for a precise period of time and it is removed, and a next batch of food is taken for irradiation. The cell in which food is irradiated is then unloaded and another batch is loaded and irradiated. Whereas in continuous irradiation facilities, food is passed through the cell at a controlled rate calculated to ensure that all the food receives exactly the intended dose. So the picture shows, the picture shows the continuous irradiation facility. Okay, you can see that continuously boxes of foods are moving. Okay, every food box is exposed to irradiation for the required amount of time and dosage. Batch facilities are simpler to design and operate than continuous facilities, and they are more flexible. A wide range of dosage can be employed and they are well adapted to experimentation when compared to the continuous facilities. Whereas continuous facilities are better able to accommodate large volumes of the product, especially when treating a single food at a given dose. So if you are taking one particular food, if in one particular in one particular industry, so if it is an apple industry, the food is apple, you are using only one dosage, right, for all the apples. So in such case, continuous facility is very useful because you put that dosage and just send different boxes of food samples. Continuous operations are usually preferred in the food industry, partly because they offer a significant economy of scale. Both machine and radionuclide energy, that is both machine and man-made, that is radionuclide energy sources, must be installed in a shielded cell specially designed to prevent exposure of personnel who is handling the food to radiation. So these radiations are not good for us. So whatever is happening to the DNA of microorganisms, that can happen to our DNA also, right? That's why these sources should be installed in a shielded cell, okay, controlled and shielded cell. A machine source is simpler to operate because it can be turned off when personnel need to enter the cell to load the product or to carry out servicing and maintenance. Whereas with a radionuclide source, radiation is produced continuously. There is no way to to turn it off until one source is finished. It is necessary, therefore, to provide a separate shielded storage space into which the source can be withdrawn when personnel have to enter the cell. Okay, how do we identify if a product which we are taking from the market is irradiated or not? So for that you have an irradiation symbol along with an irradiation code that can be treated with a radiation or treated by radiation. Like this code, the label you will have on the food. Okay, the symbol for irradiation is called as radura or radura. Okay, radura. So this symbol, the green symbol you can see, is the radura or radura symbol. Bulk foods such as fruits and vegetables are required to be individually labeled or to have a label next to the sale container. So if you take some strawberries which are packed in different boxes, so each box has to be labeled. And if you are selling some big fruit like mangoes and all, so every food should have that label that it is irradiated. The FDA does not require that individual ingredients in multi-ingredients foods, like if you have irradiated the spices, so that spice if you have used in some processed food, so you need not label it. It is important to remember that irradiation is not a replacement for proper food handling practices by producers, processors, and consumers. Irradiated foods need to be stored, handled, and cooked in the same way as non-irradiated foods because they could still become contaminated with disease-causing organisms after irradiation if the rules of basic food safety are not followed. So these are some irradiated foods with the labels. Okay, so this is the strawberries. The whole box is labeled with irradiation symbol and the label is named as treated by irradiation. Okay, irradiated. So in this you can see the mango labeled as irradiated to protect the environment. Okay, so and the last picture is to show that on the right side it is the irradiated potatoes and onions which are not sprouted after keeping for 2 weeks. Okay, so on the left side it is the non-irradiated food. So if the food is not, the vegetables are not irradiated, then it will undergo the sprouting naturally. So that's all about the food irradiation. If you have any query, you can contact the number on the screen. Goodbye for today. Continue your studies with IIOCS.com Food Tech Club. Thank you.